Just thought I'd press that before I forget. Going to have a discussion about the assignments. So I thought I'd wait one more minute to see if a few other people come in. Okay, assignments are in. You see the solutions to part A are posted. And I have some polls for you before we have a little bit of a discussion about the assignments. Here comes question number one in the series of three polls I'm going to ask you. I'll give you a minute. Okay, that seems to have stabilized with most of the respondents. And I can share the results. So the sort of the rule of thumb for courses is you should be spending 3 hours on the course material for every lecture hour. So with that, you should be spending sort of 8 or 9 hours on the assignments every week. Okay, so obviously there's a mismatch. Now, I'm going to start another poll. And when we have that, we should be in a place where we can have a little brief discussion. Okay, here we go. Okay, well, we can end that, and you can see this is all anonymous, by the way. I think I've clicked on it also. It's anonymous reporting. Not surprised. Right, this class typically attracts a strong group of students from honors physics and engineering physics. So that's a sort of grade expectation that I'm thinking of. Now I've got one last poll for you. Oh, did I share the results? I can't remember if I shared the results. Okay, I'll give you a couple seconds to look at this just in case. Oh, and by the way, the guaranteed mark of 55%, let me spell out for you. It's if you engage with the material in any way, that is a non-zero mark on at least 6 out of the 11 assessments. How about that? I'll make a concrete call on what that means. Okay, and I got one more poll.
How do we know if we got close to 100%?
Sorry, what's that?
We don't have our marks back yet, so like, how do we make a call on this?
No, this is on in general for every course that you take at UBC.
Oh, okay.
Yeah, okay, yeah, good question. Okay. And I can share the results. This is just highlighting a little bit of a difference in the format, of course, with this course from what you're used to. So, hey, you can look at this and go, 57% of people are expecting to get close to 100% on the assignments. Well, the assignments are the course mark in this class, right? Okay, so there's a few midterms thrown in, but they're really just assignments with some time pressure because they're take-home midterms. And I'm going to drop the lowest mark, so maybe there's only one midterm in there. With marks based entirely on assignments, I have to add some difficulty to the assignments. And that means I am expecting, and you can see by these numbers and the marks that you think that you might get in this class, you are also not expecting to be able to do every question on every assignment like most of you are used to doing. So that's part of the story. Of course, where I had intended the real difficulty to come is in the Part B questions. And I think that's where I can make some adjustment. I'm going to make those as hard as I can think of Part B questions, right? That's a deciding line between 80 and 100% mark, right? So I think I can ask some hard questions. Maybe people will make some start on those and get a mark or two, and that's what I'm expecting will be the maximum for most of the people taking the class. But I will try and adjust the Part A questions so that there's at most one kind of difficult question on there. And from what I heard, many students found all or almost all of the questions on the first assignment difficult. You notice I've put an easy first question on assignment number 2. So that's the start of my adjustment, and I can that I can continue to do. Okay, and I'm getting something in. For homework, 1, part B was easier. I think there was just a lack of background knowledge that most have somewhat caught up to speed on. Okay, good, that's good.
Would it be possible in the future, if there's an error in the assignment, for you to update the assignment? Because I know that this happened to some other people. I'm not sure how common it was. I missed your announcement, so I spent like as much time on problem 3 as on the rest of the other assignment because I did it. And then when I got to seeing what the limit was, it didn't make sense, and I thought I was doing something wrong. And I think like I kept refreshing the assignment, hoping that it would change. And then like on like Friday night, somebody was like, "Oh, he sent an announcement," and then
I can do that. What if I just put a correction on the assignment page? Would that be enough?
yeah, that would be great.
Okay, yeah, I'll make sure and do that.
Thank you.
So I think there was enough concern about this from the students. I want, that concern to be resolved. That's the sort of move that I'm going to make on my end. I'll say this can be an open mic kind of session. So if people want to have add any comments, I would say do so now before we start the lecture.
If I could just add something, I think the big issue with the homework was that there were a lot of like little math tricks that we had to figure out. And the problem is with those, if you can't figure it out in that moment, you spend so much time just staring at the problem, trying to get where to go. And in my opinion, that's not something that really helps with student understanding. And in reality, it can be really frustrating and time consuming. So for example, there was the one question where you had to use the trig identity. And if you had just written like in the question, note, this may be useful, I think it would have saved at least me a lot of time and a lot of confusion, because I think this might just be me, but when I get to a point where I get stuck on a problem, my assumption that is, oh, I must have messed up somewhere. And then you end up trying everything a different way. And then eventually you figure out that you need to use a trig identity, but it's just a lot of time wasted that I think could be better used. So maybe just some intermittent clues in the questions, especially if they're really wrong, or not really wrong, that's what I mean, really long, so that we know that we're on the right track, I think would be really helpful. And you could still keep a similar difficulty of the questions, but just having some of those like intermittent or mid-step, like, oh, this is the little math trick that might be useful in this question, I think would make a huge difference.
Let me say I'm happy to do that for part A, questions 1 to 3. How about that? And after that,
yeah, I'm just talking about part A.
I'm going to say I want to test some of your math skills.
Can you hear me?
Yes, I can.
Oh, okay. Can I actually jump in as well? I think that we have Piazza for like if we have questions on a specific question, I think Piazza would really help. Like if people just use the Piazza properly and said like, I'm having trouble stuck at this step kind of thing. Does somebody want to give me a hand? I think we do have the resources to do that. And I don't think that having a specific, this is step by step, here's the trig identity you'll need, that kind of ruins the course. I'm being a little bit of the devil advocate. Probably people are going to hate me, but I think since the course is a math 400, like it's a 400 level course, we're supposed to be expected to know knowledge from all previous courses and apply it together. I think it's actually kind of fair. However, in the first assignment, what was missing was just a background knowledge from previous courses. The only like Green's functions I've ever seen were from that little half a page thing from you, but obviously I had to solve and like learn Google how to do it, which I think that was the main problem. People just didn't really have the background knowledge. And this is in partial because I think the course that I took with a lot of other people was like Math 257. It was interestingly taught to the sense that they skipped a lot at the end. And I feel like now that they skipped that, I kind of wish they hadn't skipped that. But in general, I do think that after showing the polls, you did have a valid point. So I just want to say this kind of to everybody in the class. If we're being graded out of 100% and most of it is going to be the homework, it's kind of fair that you don't get 100% on every assignment, even though if you don't get 100%, you feel like garbage, like me. So.
So that's Lewis saying that, by the way, Lewis down there.
Oh God, why would you do that?
Yeah, Lewis, we all hate you.
We can tell your name lights up. Don't worry about it.
It's okay. It's okay. I don't get 100% of assignments anyways.
Just one thing I want to add as a counterpoint to that is
Sure.
that it's, I agree that it can be worthwhile to have us figure out these math tricks for ourselves. But sometimes if they happen too early in the question, people have the knowledge to solve the later parts. For example, going back to question 3, I was stuck for a long time at trying to use to solve the trig in a way that I could prove things. Once I got there, proving the actual intersection of that root of where lambda would be wasn't that big of a problem. So I think that being careful that I agree that to an extent we should be able to find those math tricks. It does stop us from demonstrating knowledge we do have that might be more relevant, of course. So if they come early in the question.
Okay.
I agree. The only other thing I want to say is to everybody, if everybody gets 100% on the assignments aren't going to be worth the majority of the mark then, because the grading average can't be 90% in a math 400 level course. Otherwise, I'm pretty sure Brian will get in trouble for making it too easy. I don't know, but just, yeah.
There's the oral exam. I was sort of hoping not to do an oral exam with 75 students, but okay, if that's what happens.
Gosh, I was hoping it would be a French one. I particularly enjoyed those.
I think
But hey,
If
what
I,
can you do?
if I could just add one little thing, I think that I agree with Lewis. I get what he's saying. I think for me, I would have appreciated if the homework was, this is going to sound odd, but a little longer with each question being shorter. Because I found the problem is with each question being worth so much, when you get stuck, it's not like it's, oh, I can just like leave this one for now, or like, oh, I'm not going to be able to figure out this little question, not that big of a deal. It's like, this is a big question. This is worth a lot. It's like the equivalent of a full question on a midterm. So I think it puts a lot of pressure on us to figure them out. And if you get stuck early on, like Julie said, it can really take a toll on our time. And I agree that we should be able to figure out all the math tricks, but we're also full-time students and we've got all of our other courses to think about. And I think that is important that we're able to spend time on the material that's relevant and not material that, although we should know and be able to use, may not actually be the focus of the course.
Okay, I think this has been a good discussion. I've talked about some of the adjustments that I will try and make. Again, the adjustments will sort of be questions 1 to 3 on part A, and then difficulty will be ramped up in some of those later questions. Any final thoughts before we go on with the material?
Yes, I have one small thing to add, and it was sort of alluded to before, but we didn't really cover, like a lot of us haven't taken a course on Green's functions. So it was a completely new topic, and we had, I think it was at the end of lecture 2, there were like 20 minutes or so dedicated to that, but I felt that I didn't really feel as confident with that material as I would have liked going into the homework. So if we maybe, I don't know, had like some extra questions on the side. I mean, you don't even have to cover them in class, but if there were just a few with solutions so we can make sure that, you know, we're really confident with that. Because I was reading that Green's functions can be used in a lot of examples to simplify things. So I'm assuming it's going to come up again in the course, and I want to feel more confident going into the homeworks in the future.
We're going to see some other examples. They're quite classic. Now, the sort of detailed things on Green's functions for one-dimensional boundary value problems in all of their generality, that's Math 401. So you saw a couple, and you're going to see the Green's function for the heat equation in an infinite space case. You're going to see the Green's function for some other problems in infinite space case. These are sort of idealized things, sort of the vanilla of Green's functions is all you're going to see from now on. And take Math 401 if you want to see more Green's functions after this.
Okay, thank you.
The other thing I wanted to mention is what I'm seeing is we have kind of 3 sets of expectations of what homework means. You know, you go to something like a Mech 375 heat transfer, and it's very much your homework is to repeat and reinforce what you're taught in lecture. And then there's so the idea is not to assess, but simply to practice. And then there's other homeworks where you're being assessed, but you're being assessed on explicitly course material, whereas these homeworks seem to be, we are being assessed on the course material and previous course material applied to that. So there's
could be the last course that many of you take in mathematics. So I guess I kind of want to use it as an excuse. one
absolutely no. I think it was a matter of
prior motion.
A matter of conflicting expectations from various points of the class, which is a fun balancing act you get to play. So we appreciate that you're willing to listen to us.
Okay, well, good. I'm always happy to listen. You know, this is a course where it's a terminal course at UBC. So, you know, what you actually take out of this, you know, there's no other course that depends on this material, but it could actually be quite useful in your careers as you try and make sense of mathematical models of things. And so I'll give you as much as I can to help you with that in your future. Okay, I make a call a couple of times for, are there any last comments? And there have been, so I'll make that call again. Okay, if not, let's get back to some of the material. I'll get other Brian to share his screen. Let's have a look. Okay, so at the end of last lecture, we were still looking at vector problems. Oh, whoop. And we were looking at a vector problem with no data. This is the homogeneous problem. This is describing a system without any additional forcing, just how it naturally behaves if it is evolving from some given initial conditions. We were looking specifically at the case where A was symmetric. Where we get this nice eigenanalysis properties that we can use to write forms of the solution. So I've got eigenvalues are real, and I've got a basis of orthonormal eigenvectors, Vj. And remember, you know, you've seen this a couple of times without the formal statement, but okay, there was a great question that came from a student in last lectures. So you know you got this Duhamel's principle, which basically says if you can solve the initial value problem, then you really understand how the problem with forcing behaves. And I'm going to repeat this question that came from a student because I thought it was really nicely worded, better worded than I had used. And it is so we treat any forcing functions as a continuous superposition of initial conditions, right? That's a nice statement of Duhamel's principle. Okay, but we haven't got any forcing now. We're just looking at this problem. And we know because this is a basis, we can write the solution at every time. It's just a vector with n components. And so I can write it in terms of this basis of eigenvectors with some time-dependent coefficients. And if I put this form in here, right, then I end up with the sum of the time derivatives. These vectors aren't time-dependent. I got some funny business going on with my pen. And over here, when I take a times this, I just get lambda j coming in because a times vj is lambda j. Right, it's a eigenvector. Right, and then because this is a basis, the only way that these guys can add up, right, is if the coefficients of the basis vectors add up. So I end up with these really simple problems, just exponential growth and decay, right? There's no complex eigenvalues here, so there's no oscillatory behavior. And then I get the solution is a, okay, my pen is doing something funny. It's whatever it is at time 0, e to the lambda jt. And this thing, this is easy to work out, right? If I look at u at time 0, right, that's u0. I can get the initial conditions from these guys. These guys are orthonormal, so if I take vi dotted with vj, I get 0 unless I equals j, and vi dotted with vi is a 1, right? Because I've normalized them. And so these guys, aj at 0, this is just, if I take the inner product with okay, it's doing funny things with my pen. I've got something set up. Oh, now I see. Ink, I've pressed something, ink to shape. Okay, there we go. Oh, technology, so helpful. This is just, I take the initial data and I take the dot product with vj. Okay. Okay, so that was fun, right? That's back to Math 215 or something like that. Let's look at the heat equation now. Right, I'm going to look at the same case where I've only got initial conditions, no forcing. But, you know, I've got Duhamel's principle. I know how it's going to go, right? I'm going to have initial conditions. And I've got to give boundary conditions. I'm going to have the, this is u of x and t. I'm going to give boundary conditions that are just the easiest ones. Remember, we separated the heat equation out into the sort of 3 different types of problems. There's the initial condition problem, there's the interior forcing problem, and there's the boundary condition problem. Really, two types of boundary conditions, one on the right and one on the left. But you can think of treating those the same. That's the one where the mathematics gets the most difficult. It's a Laplace transform problem. And so it's something I'm going to leave until later. Okay, well, remember, I've written this before, right? I can think of this as some sort of operator, and this includes the boundary conditions. Right? And I've already worked out that L is symmetric in the inner product of functions with the boundary conditions. That looks like this. Really, that's a nice extension of the Euclidean norm. Instead of multiplying the components together and adding them up, I'm multiplying the values of a continuous function together and integrating them, right? Right, and I know that the eigenvalues are lambda j is minus, why don't I use n? Minus n squared pi squared. And the orthonormal eigenfunctions are these normalized sine series. L does not include the initial conditions. Okay, no, it's just L is just the boundary value part, right? Okay, just like up here for this vector case, the eigenanalysis of A doesn't include the initial conditions, right? It was just a separate calculation. And then afterwards, you can work out how the initial conditions project onto the eigenvectors, and you understand how those components behave. And exactly the same way here, right? I'm going to have a solution, u of x and t, right? I know that at every t, this is a function of x with the boundary conditions 0 on the two ends, so I can write it as a sine series with some coefficients. And if I put that into ut is uxx, right? What do I get? I get the sum of n equals 1 to infinity a n dot. When I take the second derivatives here, well, that's just applying L to this thing. So I get minus n squared pi squared a n phi n of x. These are orthonormal functions. So the only way these sums can add up to the same thing is if the coefficients match 1 by 1. So I've got a n dot is minus n squared pi squared a n. Right, well, that's a simple exponential decay, right? So I know that a n of t is whatever it is at time 0 times e to the minus n squared pi squared t. And I know that a n of 0, just like up here, right? All I have to do is to take the projection onto that eigenvector. It's orthonormal, right? All I have to do here is to write the initial conditions as a sine series and take that sine coefficient. So this is the integral from 0 to 1, the initial conditions times sine n pi x dx. So if I put it all together, right, I have a solution, u of x and t. Remember, this is the solution to the initial value problem only, right? Well, it's a sum, right, over the sine series. right? It is got this coefficient. So now I'm going to use a dummy variable. That's just a number. Times sine n pi x. Right? Okay, so this is pretty nice, right? Oh, I forgot the most important part. Right? I've got an e to the minus n squared pi squared t here. Right? Times a sine n pi x. So now we can have a little bit of discussion around this form. Right? Well, what can I say? I have a bunch of components. Oh, there's a question that didn't come through. Yes, I forgot the square root of 2 here and the square root of 2 here, which I'm going to combine into a 2 here. Okay, thank you very much. One of the things, of course, I want to discuss is this is a bunch of decaying terms. So if I look at the limit as time goes to infinity of this solution, I just get 0. Right? Well, okay. So if you've got a metal rod and you're holding both ends of the rod at 0 temperature, and heat's allowed to diffuse in the rod, and there's no external heating, there's no F, well, yeah, it's going to cool off to be at 0 temperature eventually, right? Okay, that's a good thing to notice, right? What's another good thing to notice? Another good thing to notice is that the n equals 1 is the slowest decaying term. So e to the minus pi squared t, right? This is telling you there's a time scale for the decay, which is like minus 1 over pi squared, right? And this is why in the assignments, when I've asked about the eigenvalues smallest in magnitude, I'm thinking of these kind of problems where there's decay, and all the other terms decay faster. And so the lowest order eigenvalue, the smallest magnitude eigenvalue of all the negative ones, is the most interesting one. And sine n pi, not n pi, sine pi x is the shape of the slowest decaying term. So that is the most interesting shape, right? If you wait long enough, okay, well then the temperature is going to be 0, right? Okay, so that's a good thing to know. If you've waited a little while, then this is going to be the thing that you see. Everything else has decayed faster, right? So if you think of a hierarchy of things of interest, well, okay, this is the most interesting thing, maybe, right? And then after that, it's this term. And then, of course, if you're really interested in some sort of fine details of what's going on, then the next term will tell you the time scale for how long you have to wait until you really only see this one left.
I just wanted to add that you covered this in Math 4.1 as well.
Oh,
Well,
okay.
sort of.
Good. Okay, and that's okay. What I wanted to say here. Now, I guess there's something I want to interject, and maybe this is the right place to look at it. Okay. What if I just change the sign on this equation? What if I said ut is minus uxx? This is the backward heat equation. Because I've really just changed the sign of time, right? If you let time go backwards and write t equals minus t, this is what you would get, right? Now I should put a big red box on this. This problem is ill-posed, right? It's not a physical model. So I can just tell you exactly what comes out, right? If I have initial conditions, I'm going to get the sine series, but instead of exponential growth or exponential decay, I'll get exponential growth. I'm just changing the sign of the eigenvalues. So I can just say that u of x and t, I'm putting this all in red. This is, if your model ends up with a problem like this, you've got a problem with your model. I'll just say that. So this is going to be the sum of n equals 1 to infinity. Let's remember the 2 this time. I've got the integral from 0 to 1 sine n pi s times u0 of s ds. And I've got an e to the pi n squared pi squared t times sine n pi x. Okay, have a look at that. Right, and this is where you can go, I can see right away that this is an ill-posed problem, right? Right. If I look at some time, big T, right? This term, that's e to the n squared pi squared big T, goes to infinity as n goes to infinity. So if I'm wondering how the initial conditions from this component affect the solution at a later time, it is unbounded dependence. So this says arbitrarily small changes in U0, right, make arbitrarily large changes in the solution. So this is ill-posed. Okay, so this is not a this is not a good problem. There's a question coming through on the Slack channel. Do mathematicians use backward equations in the field to determine previous behavior of physical systems? Well, some systems are not ill-posed, going backwards in time, right? And so there you can have reversibility, right? So you can say, you know, I can run this equation forward or backwards in time. and the backward part is not ill-posed. But the backward heat equation doesn't make sense. Now, I guess I can highlight that a little bit. If we go back to this equation, this is the forward result, right? If I were going to take the solution at time big T and say, I can work out what the solution at time 0 is, well, then you have to get all of these coefficients right? And the trouble is, all of the information from those large n coefficients is exponentially small by the time you get to a later time, right? So you're trying to take some really small information and work back to some reasonable estimate of what things were like at time 0, right? And of course you can't do that. There's another question. Okay, why do arbitrarily small U0 changes result in large changes in the solution? Well, I can pick this function to be whatever I want. So I can make it so that it has non-zero coefficients for every n, right? And as soon as you do that, then I've just got some number here, right? Being multiplied by something arbitrarily large. So I think that should be clear. If you've got a number 0.01, but you get to multiply it by an exponential as big as you want, okay, right.
Well, the way I was thinking about it was you have this, like, say you pick some number, like number 2 or whatever, in front of that, and then you pick number 4. You've done an arbitrarily small change to U of 0, but you basically got the same result, right? But that's not the way to think about it. It's more so just like, what is U of 0 and what is the solution doing?
Okay, good. Maybe one last thing. Maybe I'll put this on an assignment question. Okay, maybe I won't. If I have this solution, another question comes in. What if you take I instead of a minus sign? That's getting to the Schrodinger equation, and that is reversible, right? Because if you put the I in, then you get oscillatory behavior, right? Well, okay, now I have to think here for a minute. You get arbitrarily fast oscillatory behavior. Anyway, that is a well-posed problem and reversible. So there you go. We're not going to do the Schrodinger equation in this class unless there's a huge bunch of people that want to see it, and then we'll do it at the end instead of free boundary value problems. If I look at this thing, the last discussion, let me get a different color. Here's green. I can write a Green's function out of this, but not a particularly useful one, okay? People ask about Green's functions. Remember, I'm describing those as the map of the data to the solution. So my Green's function here should be taking the data S and telling me what the solution is at some later time, right? And then I would multiply by U0 of S, and I'd integrate over the initial data, ds, and I would get the solution U of X and T, right? If I had a Green's function for this problem, this is what it would be, right? Well, now I'm just going to pattern match, and I can get G of X T S, right? Well, I'm integrating something with the S, so that's a good start, right? What is it? Again, this is not particularly useful, right? It is 2 times the sum n equals 1 to infinity, sine n pi s, sine n pi x, e to the minus n squared pi squared t. Right, so a Green's function written out as an infinite series is not that helpful, right? Because what we liked about the Green's function before, it was like an explicit map that you could say how the data affected the solution. And this is not it, right? This is something which is formally a Green's function, but is not helpful in the same way that the other ones we wrote were. People ask about Green's functions. Is that sort of clear? I'm just pattern matching something which is the map from the data to the solution, and I'm working out what that has to be from this formula we worked out for the sine series. Oh, there's a question. Does the series converge to anything? Yeah, it has a nice convergence property. And of course, one of the things that helps here as you're looking at the convergence is all of these terms decay very quickly with n for times bigger than 0. So yeah, okay. So it's a very fast convergence series. It converges to something, okay, which doesn't have a nice form in terms of functions that we know and love. Okay, well, let's go on to the forcing function, okay? I'll go a little bit quicker here, right? I've got the same eigen values and eigenvectors that are normalized and orthogonal, right? I can write the solution in terms of those eigenvectors. And I put it in there, and I get the sum of aj dot vector is equal to the sum of aj lambda j vj. And then I've got this f. Well, this f, which is dependent on t, I also want, oh yeah, derivative, thank you. That I also want to write in terms of an eigenvalue expansion. So I'm going to put this as fjvj. Oh, I better not use fjj, where these guys are just the inner product of f of t with vj, same as before, right? So then I get aj of t. Well, let me write out the lambda j aj plus bj of t. Right, and then we've seen this equation before, right? It's just a constant coefficient linear problem, and this is the first time we saw how Duhamel's principle worked. But let me just say this is just, it's now the integral in S. It's e to the lambda j t minus s f j of s. And then if I want the solution, it's just okay. Let's see what this looks like for the heat equation. with 0 initial conditions, right? This is problem number 2. Problem number 1 was the problem with initial conditions but no data. Problem number 2 is the problem with data but no initial conditions, 0 initial conditions. Okay, well, I'm going to want to write f at x and t in terms of a sine series at every t. Oh, here I can use fn because f is not a vector. Right, where this, oh, come back, where this fn of t is just the square root of 2 times the integral from 0 to 1 of f of x and t sine n pi x dx, and maybe I better use s. And then I can put in my sine series solution. I now know that an at time 0 is 0. I can put that in here, and I can equate terms term by term in the sine series, where I get an dot. When I take the second derivative of this thing, I'm satisfying the boundary conditions. Oh, I better put in that I've got I've got the 0 boundary conditions I had before. Just so you know, we're on the same problem that we had before. Here I've got the minus n squared pi squared an. And here I just add in this forcing term. Well, this is the same thing that we had up here. Well, except we got an infinite number of these, but okay, they're all separate, same as up above. Okay, I don't know what my thing is doing here, but I'm going to write out that an of t is just the integral in ds. I've got the fn of s, and I've got the e to the minus n squared pi squared t minus s. Right, and again, this is just like the excellent comment from the student from last lecture. The forcing is like a continuous superposition of the initial conditions, right? It's like fn at s, we're treating like an initial condition at s and seeing what it's like at time t, right? And superimposing all of those infinitesimal contributions to get the solution. That's Duhamel's principle. But I haven't formally used it here. I just derived this this expression, and I'm calling it Duhamel's principle. Okay. And here you can see that the n equals 1 eigenvalue is the most interesting here too. Okay, because if you're looking at components of the forcing, the sine series components of the forcing with larger n, they also decay faster in time, right? So any oscillatory component to the forcing doesn't persist as long as the kind of sine series shape of the forcing. That's the one that lasts the longest in terms of its influence on the solution at later times, right? And so this is, you know, the series solution part of the course. And now you see for these diffusion problems, heat equation type problems, parabolic equations is the class that they fall in. This is why you see that there is some important information coming from the eigenvalue problem that you can solve for the spatial part, right? Because it's really governing the parts of the solution that will persist the longest in time in these time-dependent problems. Okay. I'm going to do something a little bit different to end this lecture. We've got the sine series. I'm going to show you something a little bit different. Remember, this is how I'm going to draw the problem. Here's the theorem. Right? This is something that's giving you information about the solution that would be hard to find from the sine series properties. This is called the maximum principle. Let M, this is going to be the maximum of the initial conditions and 0. Okay, so if all the initial conditions are negative, then M will be 0. But if there's some positive temperatures initially, then M will be the maximum positive temperature initially. Now here's something that makes sense physically, right? Then the solution to this problem satisfies U of X and T is less than M, less than or equal to M for all X in the interval and positive times. Okay, this makes perfect sense, right? If you've got, you're thinking about temperature, this says you cannot spontaneously, in a heat diffusion problem, you cannot spontaneously generate temperatures hotter than what you started with, okay? Okay, so it makes physical sense. Okay, proof. Yeah, this is without forcing. Okay, that's a good question. You notice there's no F here. If there is forcing, obviously you could start with the bar at 0 temperature, uniformly 0, and heat it up, right, and get higher temperatures. So this is only if it's left on its own. If you look at this equation, right, that's ut minus uxx is 0. You can almost see the argument, and there's a little bit of math work you have to do to make it actually finished, right? If there is a bigger temperature, well, it can't be on the boundary, right? Because U is 0 on the boundary. right? So if there's a bigger temperature, it has to happen in the middle. Let's look at the conditions for having a maximum value here, right? UT and UX would have to be 0 for it to be a maximum. So you'd have UT is equal to 0. UXX, well, right, if it's a maximum, right, then it has to look like this, and that tells you that the maximum, or that the second derivative cannot be positive, right? It has to be non-positive. Now, that's almost the argument, except non-positive could be 0, right? Okay, so there's a little trick you have to do to get around that. You have to consider, ooh, how's my time going? Oh yeah, I can finish this. Of course, I had a bunch more I was going to do, but I thought we had a very useful discussion at the beginning about the assignments and expectations. So yeah, I don't regret that at all. Okay, so here is the trick. You have to give a little bit of help to the second derivative argument. So there was my u. Now I'm just adding something small to it. So now I'm going to look at VT minus VXX. Well, that's UT minus UXX. Well, that's 0 by the heat equation. And then I'm going to have the second derivative of this term. That's minus epsilon. That's less than 0. Okay, so now I can use the argument. I've got VT minus VXX is less than 0. So that tells me V cannot have a maximum value in the interior of the domain. Right, because if I did have a maximum at the interior, VT would have to be 0 and VXX would have to be negative, right? So, or it would have to be non-positive, and then this doesn't add up, right? So I have excluded, where's another color? Oh, let's do the rainbow one. I like the rainbow one. Where is the rainbow? Where did it go? Oh, there it is. Okay, so I've excluded V having a maximum anywhere in here, and so it has to have a maximum on one of these boundaries. Oh, let's go back to black. So V must have a maximum at either one of the 3 boundaries of that domain, left boundary. So that's where V is 0. Right boundary. Well, remember, V is U plus this. So at the right boundary, V is epsilon over 2. Or the initial conditions. And that's where V has to be less than or equal to M plus epsilon over 2. So I've got U is V minus epsilon x squared over 2. That's less than or equal to V. And V is less than or equal to M plus epsilon over 2. Right, because M is at least 0, because we threw that into the maximum. So this doesn't give you anything new. Right. Okay, so now, of course, now you let epsilon go to 0, and you get U is less than or equal to M. That's the result that you're after. Okay, and a similar argument. And you can just do this maximum principle on minus U, right, to get it. Shows that U of X and T is greater than or equal to the minimum of all of the initial data or 0. Okay. Well, okay, this is certainly a result that matches up with your intuition about how this problem should behave. And again, this is one of those things where you have some back and forth between the model and the mathematics. You may have, you may have a strong physical intuition that the model should have this property, and that it has it. It gives you some confidence that this is modeling the kind of physical behavior that you're hoping for. Or maybe you were wondering, whether you could have spontaneously formed hotspots in the system, and you believe that the equation describes the system, and so this gives you the insight that it doesn't. By the way, this is an interesting kind of result that's different than what we had before. I mean, before we had the sine series solution, and we could look at it and understand some of the behavior of the system. But this is a result that we get without knowing the solution. Right? I don't know what the solution is for all of the initial conditions I've written down there, right? And so this is a different kind of result. It's what's known as an a priori result. It's a result you know about the solution before you find it, right? And so that's interesting. By the way, this also shows that the problem is unique and well posed, which you could also get from the sine series solution. Because if I've got initial data U0 of X, giving a solution U of X and T, and I've got initial conditions that are different, giving me a V of X and T. Then if I look at the difference between these solutions, right, this solves the heat equation with initial conditions U0 minus V0. Well, so I know that that solution has to be smaller than the initial data. So I already know at every later time, if I make small changes in the initial data, I'll have small changes in the solution. The uniqueness comes from, well, if I start with the same initial conditions, then the difference here is 0. And so there can't be a solution, two solutions that are different later on, right? So kind of a nice thing which you can prove in any number of different ways, but this is the easiest one to see after you've got the maximum principle that the heat equation is got unique solutions and it's a well-posed problem. 1045, 1046. That seems like a good place to stop. We're going to round up this discussion next time with a statement of the Sturm-Liouville theorem about boundary value problems and how it affects these kind of things. And there's an example in the notes that's similar to assignment 1, question number 3. And I won't go through that. That's similar enough to assignment 1, question number 3, which you have the solutions for. But there's a fun result where we can use a asymptotic technique to get some insight, and I'll show you that one, and then we'll move on to higher dimensional problems after that. We'll have some Bessel functions coming up. And one of the polls I guess I should ask is, are Bessel functions your friends? Okay, they're not my friends really, but we'll try and at least get acquainted with them. Okay, I'm going to stop recording